Okay, so in this video I'm going to have a look at a more formal definition of limits, and in particular I'm going to have a look at the epsilon delta definition of limits. So epsilon is represented by this letter here, and delta is represented by this letter here. Now this is our function here, and I'm going to call it f of x, and I'm going to call this value here a, and the limit at a, the limit of f of x, the limit of f of x as x approaches a then is going to be equal to L, this value L here. Okay, so what are epsilon and delta then? Well, epsilon is any value you choose to be on either side of L, if you like. So how close do you want to be to this limit? You want to be epsilon close to it. So in other words, say you decide, well, I want to be 0.5, say this was, I don't know, 5 here, and you said I want to be within 0.5 L, well then epsilon would be 0.5, so you're looking at 5.5 and 4.5, so you want to be within that range of the limit. So that's your epsilon value there. So in other words, let's say pick this is epsilon here and here, so this would be L plus whatever value epsilon you chose, and this would be L minus whatever value epsilon you chose. So if we come across here and go down, this value here would be A plus our delta, and this value here would be A minus delta. So in other words, you pick a particular value, epsilon, and you say I want you to be within, I want to try and be closer than that value epsilon to the limit. And I will say, well, okay, I can find a particular delta here from A, within which I can find an x value that will actually give me a value closer to L than epsilon. So the way I would write that out formally then would be, I would say given, so I'll just write it out here, given any epsilon, so given an epsilon, has to be positive of course, so given some value epsilon, we can find a delta, which also has to be positive of course, such that I can find an x value from A, some x value in here from A that's less than delta. So the distance from x to A is less than the distance from delta to A, so there's some value in here, in other words. Then the distance from f of x, so when I stick this value here into the function, I get a y value. That value from the limit will be closer than epsilon is from the limit. So in other words, the x value will be somewhere in here. There's always going to be some x value within delta from A that will give me a y value within epsilon from L. So there's always going to be, there's all these x values here that will give me y values that are actually closer to the limit than epsilon is, than the epsilon you originally gave me. So this is the kind of formal definition, if you like, of limits. So whatever value epsilon you give me, I can always find some delta, which is a certain distance from A, and within that distance I can find an x value that will actually bring me closer to the limit than your epsilon value that you gave me initially. Okay, so let's look at a practical example. So let's take an x and y axis again, and we'll just draw a graph. So let's say we have, let's just see what we got here. Okay, so we're going to do f of x again, and let's go up here in twos, let's say 2, 4, 6, 8, 10, and 12. This is our y-axis here, and this is x. And let's go out here in, let's say, 1, 2, 3, 4. 1, 2, 3, 4, 5. Now our function here, again, we'll do a piecewise function here. So it's going to be, let's say we'll pick a simple one, 3x, when x is not equal to 3. And let's say it's going to be equal to 3 when x is equal to 4. So let's just draw that. So we'll do this part here first. Let's say when x is equal to 4, y is equal to 3. So that's going to be there somewhere. Other than that, it's going to be just a straight line. And let's see, when x is 0, so 3 times 0 is 0, 3 times 1, 3, 3 times 2, 6, 3 times 3, 9, roughly here, 3, 4 is 12, but when it's 4 is 3, 3, 5 is 15, so it's going to be 12, let's see, I'll just keep going up here, 12, 14, and 16, so 5 is going to be 15, so oops, battery is running down. Okay, so it's going to be roughly here. So our graph will look something like this. Oops. So it's going to look like this, but there will be a gap here, of course, at 4 here. Okay, so that's it. So let's have a look then at doing a proof here. So what we're going to do here is we're going to look at proving that the limit of our function f of x, this is f of x here, the limit of f of x as x approaches, let's say, 3, is going to be 9. So in other words, 3 3's, obviously 9 here. Okay, let me just plug this computer in. Out of battery, there we go. Okay, just call it in time. Now, okay, so this is what we want to prove here, that the limit of our function as x approaches 3 is 9. So let's use our definition here of our limits, our epsilon delta definition. So let me just write it out first, and then we'll see if we can do it. So our formal definition, what we want to prove really is that the modulus of x minus a, that's going to be less, which is less than delta. If that's true, then the modulus of f of x minus our limit is going to be less than epsilon. This is, if we can show that this is true for this particular function here, then we've proven it. Okay, so we want to do this here. So let's stick in the values that we've got. So I'm just going to start here on the left hand side. So we want to show that our x minus our a, now remember our a here is 3 as x approaches 3, so we're looking at this value here as x approaches 3, is going to be less than delta. Then f of x, or f of x minus our limit, we're saying our limit here is 9, is less than epsilon. So if we can show that this is true, then we've proven this part here. So let's do that. So what I'm going to do is just take the left hand side of this here. So I'm just going to take the left hand side, see if I can turn it into the right hand side here. So let's see what we can do here. Well, what I'm going to need to do is change this into a 9, if you like. So I'm going to have to really multiply this to left hand side by 3. So I can do that. I'm going to do this here. 3 times the modulus of x minus 3 is less than 3 delta. So 3 times the modulus of something is just the modulus of 3 times it. So I'm going to just multiply it here. So it's going to be 3x minus 9 less than 3 times delta. Now if you look at this 3x here is just our function at 3. If you look here at our original function, 3x is our function, is our f of x at anywhere but 4, but we're looking at 3 here. We were looking at an x of 3 here. So at 3, at x is equal to 3, our function is 3x. So this part here is just f of x. And our 9 here, that's just our limit. That's our limit. And remember, 9 is the limit. 9 is our limit at 3 here. You can see as you approach 3 from the left and the right hand side here, anyway, we're going to get 9, but this is what we want to prove. So we can see here that 9 here is our limit. So we're almost there. And we're saying that's less than 3 times delta. Now we've almost got the right hand side here. We've got our f of x, we've got our minus, and we've got our L, our limit here. What we don't have is this part here. We have a 3 delta where we have epsilon here. So what I'm going to do here is just say that I'm going to just change this here. I'm going to say that delta, our delta here is epsilon over 3. I'm going to define this delta as being this here for this particular function. Delta is epsilon divided by 3. If I do that, what happens here is I get f of x minus L less than 3 delta. Remember, delta is epsilon over 3. So if I put in epsilon over 3 here, the 3's will cancel or divide if you like, and I'll just end up with epsilon here. Now I've got the right hand side. So look, that's exactly the same as this here. Okay, so I've shown that for x minus a less than delta, the modulus of x minus a being smaller than delta, then f of x minus the limit, the modulus of f of x minus the limit will be less than epsilon. And I've shown it for this particular function here, allowing for the fact that delta is epsilon over 3. So how does that actually work? Well, we've done the proof. So let's say, for example, let's say you take you say, well, okay, well, I want to be within 0.5 of the limit. I want to be within 0.5 of 9. So that means the epsilon then will be 0.5. Epsilon will be 0.5. Then I say, okay, well, if your epsilon is 0.5 from the limit, I can find a delta. So my delta then will be just simply 0.5 over 3. Because remember, that's what I got here. That's what I'm saying for this particular function. Delta will be epsilon divided by 3. So in other words, I can find, once you give me this epsilon here, all I have to do is divide it by 3. And I'd say, well, that's going to be, my delta is going to be 0.5 divided by 3. So in other words, all I've got to do is say, well, my delta is 0.5 over 3. So all I've got to do is find an x value. So this is my original graph here. Find an x value within this particular delta, 0.5 over 3. So all I got to do is find an x value closer to 3 here than 3 plus or minus 0.5 over 3. So in other words, I've got this 3 plus or minus 0.5 over 3. That's my range, and within that range I can find any x value that will bring me closer to my limit than 0.5, than your epsilon that you've given me. And that's really it for the formal definition of limits.